When it comes to aromaticity, one of the key skills you'll want to nail down is identifying aromatic compounds. And there are two principles we want to follow. First, we want to have an overlapping system, overlapping ring of p orbitals. So I'll just put like that. And I'll fill in one so that we can consider them p orbitals. We also want to make sure that we have a Huckel's number of pi electrons. And I've always viewed this as an odd number of double bonds. After all, you should know that Huckel's number is 4n plus 2 pi electrons. So let's take the following example. We have this carbon anion with these two double bonds here. So what do we want to start with? We want to make sure that there are overlapping p orbitals. We know that we have p orbitals within these double bonds, otherwise you couldn't house those double bonds. But what about this lone pair here? There are a few ways to view this. One is to consider that we do have resonance here, and I could have this double bond, this lone pair move here and force the double bond to push electrons up into the carbon. And I won't draw that out for the sake of time. And we consider that since with resonance we have movement of electrons within a system of p orbitals. You could also view this conceptually as the carbon that houses the lone pair wanting to put its electrons into an aromatic system. And I'll explain that as we move on. So if we do have this overlapping system of p orbitals, we want to make sure that we have Huckel's number of pi electrons. So in this case, we know that we have one lone pair, so there'll be 2 pi electrons plus 2 from the other double bond, and another 2 from another double bond, which would be, of course, 6, since we can all do math. And another way of looking at this, I said before, you'd view this as an odd number of double bonds, or you can also say an odd number of double bonds plus lone pairs. Thus, this compound would be aromatic. And you view this as that the carbon, what I was mentioning before, this carbon right here, if it does put its electrons in to a p orbital, then we do achieve this aromaticity. And since this aromaticity is a unique amount of stability, it's favorable in that sense. Of course, determining aromaticity in some other compounds can be a little more complicated. And here, let's apply the same process with this molecule. We should notice that if we're trying to find this overlapping system of p orbitals, that we do have that achieved right here in this area of the molecule, because we have these 2 double bonds. We know that the nitrogen is playing a part in housing a pi bond through one of its p orbitals. The question comes into play, though, is that we have the sulfur here, which we would expect to be sp3 hybridized, to be tetrahedral in geometry with its lone pairs, or bent in this case. So the question becomes almost, could this compound be aromatic? So yes, the sulfur does have a lone pair to put in a p orbital to achieve aromaticity, but we need to count the pi electrons in the rest of the ring. So we know that a sulfur would be, in a way, donating 2 pi electrons, their lone pair. So we already have 2. And then we can see, okay, from this double bond right here in the ring, that would be 2. So I'll go ahead and write that back up here. And then we also have the double bond that the nitrogen is participating in, and that's 2. But we want to make sure that there are no more electrons. We want to say that this is final. Well, let's look at the lone pair on the nitrogen. If this nitrogen is sp2 hybridized, and its p orbital is already involved with a double bond, so this would be a localized lone pair, and thus it can't participate in aromaticity. Same thing over here with the sulfur. One of the lone pairs will be localized, and that's not participating in aromaticity, so I can draw, I'll say that one. It doesn't really matter which one. But now that we know that one lone pair in the sulfur is localized, the lone pair in the nitrogen is localized, the rest of the pi electrons are participating in this overlapping system of p orbitals. Thus, this compound is aromatic. And again, the key question almost becomes, could a certain compound be aromatic by achieving these sets of rules that we've set forth?